Dear students, welcome and thank you for tuning in to another video. We are still talking about phase diagrams from the material science class. In this video, we're going to go deeper a little bit into what phase diagrams are in real world. Phase diagrams that we will deal with when we deal with metals and alloys. In the previous videos, we showed one phase diagram of sugar and water when we were trying to look at materials that we use in engineering applications. Most of them are metal alloys. We're going to look into the first phase diagram. It's a simple one, but it encompasses all the criteria and the information and the level of complexity that is expected in alloys. The alloy that we're going to study is nickel copper alloy. If you remember from the previous video, we talked in order to have total solubility of these two elements, they have to have same crystal structure, very close in electronegativity, and they should have the same atomic radius. Let's dig in and see how a phase diagram will look like for an alloy. This is the phase diagram of copper and nickel. The phase diagram in general indicates phases of the mixture that we have of these two elements. It's a function of temperature and component, which is the concentration, as well as a function of pressure. We're going to assume that we have the same pressure all the time. So we're going to look at the changes in temperature and concentration. So temperature will be our y-axis and concentration will be our x-axis. If you remember, this is the temperature. We can go up to 1600 degrees Celsius for the copper and nickel mixture, and our concentration here is a percent weight of nickel, which means that at 0 point I have 100% copper and 0 nickel. Here I have 80% copper and 20% nickel. Here we'll have 60% copper and 40% nickel, all the way up to 100% nickel and 0% copper. So concentration, function of time, and this is our phase diagram. Now, these phase diagrams are called binary systems because I have only two components, copper and nickel, and we have two independent variables, which is temperatures and concentration, or components, and pressure is constant, and we are assuming it as 1 atmospheric pressure. If you look at this phase diagram, you can identify regions. And if you remember from the previous one that was about the sugar and water, we have only one curve, just like this was the solubility curve, right? Now I have two curves. This is called the liquidus curve, and the blue one is called the solidus curve. And we're going to look into these regions carefully. So in the green region here, the top of the liquidus phase, you can see that we have all liquid. So this is one phase of liquid. And below this line, the solidus line, we have one phase, which is a solid phase, a solid solution, right? And remember, when we talked about solutions, we said they are homogeneous, it's one phase. Keep in mind, this is different from mixtures. So here, this is not a mixture, it is a solution, which means that I have a solid material that is made of copper and nickel, and it's a face-centered cube. It's crystallinity, and it's solid instead of liquidus. So to summarize, I have two phases, a liquid phase and a solid phase, but I have in this diagram three different phase fields, which are regions. So this is region 1, region 2, and region 3. So in this white region here, I will have two phases at the same time. I will have liquid and solid at the same time. So this is just a description of how the phase diagram will look like. I hope that is clear. And we're going to use this phase diagram to extract information and to learn more about the composition and the structure of the material that we're looking at, given specific temperature and specific concentrations. One more thing before I finish. If you look at this copper-nickel phase diagram, the one that we showed before, this system is called binary because I have two components, copper and nickel. Also, this system is called isomorphous. Isomorphous. There you go. And what isomorphous means, that it's a complete solubility of one component into the other. And we can relate to this because copper and nickel have the same electronegativity, the same atomic radius, and they have their face-centered cube. The crystal of them is face-centered cube. So they're very soluble. Also, there's another condition. The other condition is that the alpha phase, this phase, spans from 0 to 100. And that is also another definition of the complete solubility. So I don't want to go into details into this, but keep these in mind. If you have the x-axis going from 0 to 100 for one of the elements, this is an isomorphous alloy, and that is how we're defining it. So it's either you say complete solubility or the alpha phase field extent from 0 to 100. I hope this clarifies the binary phase diagram, and we're going to use this phase diagram to solve a couple of problems and exercise problems to see how we can use it and learn more information about our material. Now, as an engineer, as a material engineer or a material scientist, you will be given the task of creating these phase diagrams for any alloy you're going to create. So if you want to create a material for a specific application, and that is an alloy, it's a mixture of two metals, you need to create this figure first. And it's an empirical figure, which means that all the data here are experimental. And you can do something like this for your project if you are if your project for the class is using metals. Thank you. Until next time.